This chart contrasts how we describe physical reality in classical versus quantum mechanics. In the classical world, defining an object is straightforward. You pinpoint its exact position on a grid and measure its velocity. But zoom into the quantum realm, and that solid object dissolves. Particles lack fixed coordinates. Instead, they exist as a spectrum of probabilities, a diffuse, vibrating cloud where an electron might eventually be found. To calculate probability clouds, early physicists relied on continuous wave functions. This required dense integrals, unwieldy machinery that fails to scale. To solve this, Dirac developed bra-ket notation. This compact mathematical language allows physicists to efficiently calculate state vectors without endless calculus. To navigate the complexities of the quantum world, physicists had to stop treating reality as a fixed coordinate grid and start treating it as a language. The architect of this language was Paul Dirac, and the system he designed acts as the underlying grammar for modern physics. We read quantum mechanics using this dictionary. Kets function as our nouns. Bras represent their mirror images. Operators act as verbs, actions performed on those nouns. The system relies on its own punctuation. Inner products bring states together to extract probabilities. By utilizing this linguistic structure, dense matrix algebra turns from a process of rote calculation into a logical, readable narrative. Let's examine the primary noun, the ket. Defined by these boundary lines, this symbol contains all knowable information about a quantum state. Mathematically, it's a state vector. The quantum equivalent of a classical arrow is this column of numbers. Depending on the system of your observation, a ket represents specific physical realities, like an electron's absolute lowest ground state or a higher energy state. Every quantum noun possesses the dual state, known as the bra, written with the bracket facing the opposite direction. To create it, you perform a conjugate transpose, laying the column vector flat into a horizontal row. Then you take the complex conjugate of its elements. In practice, if your ket contains a complex number like 1 plus I, its bra mirrors it exactly as 1 minus I. Kets and bras are two halves of a single mathematical reality, designed specifically to be combined. When a bra and a ket face each other, the notation collapses into a single closed bracket, an inner product. This operation is a mathematical diagnostic tool. It measures the exact degree of overlap or similarity between two different quantum states. When two states are completely independent, meaning they are mathematically orthogonal, their probability waves do not align at all, resulting in an inner product of precisely 0. On the other end of the scale, if you measure a normalized state perfectly against itself, the overlap is total, returning an inner product of 1. This calculation forms the probability engine of quantum mechanics. By taking the inner product and squaring its absolute value, we extract the physical chance of finding a system in a specific state. Consider a quantum coin in an equal superposition of state 0 and state 1. When we process the inner product math, it outputs a measurable 50% chance for either outcome. The inner product is the crucial mechanism that translates abstract mathematical potential into physical probability. With nouns and punctuation established, we introduce the verbs. In Dirac's language, these are the operators. Denoted by a hat symbol, these objects act upon our state vectors to change them or to extract data. Operators correspond to real physical quantities.
We use an operator for momentum, an operator for spin, and the Hamiltonian operator to calculate total energy. Under the hood, operators function as matrices. When an operator acts on a ket, it performs literal matrix multiplication against the state vector's components. This matrix action physically transforms the initial vector by rotating its position or scaling its magnitude, and ultimately outputs a completely new mathematical configuration. You can see the engine at work in this schematic. We supply an input state, the operator matrix applies its transformation, and we retrieve a modified output state. The ket is the physical object, and the operator is the action applied to that object. Operators provide the mathematical bridge between a static description and the dynamic reality of physical measurements. By combining these nouns and verbs, we construct complete thoughts. If an operator acts on a definite state, it reveals a hard physical number, known as an eigenvalue. If the state vector remains identical after the operator acts upon it, it is an eigenstate, and the isolated number sitting in front of it is the exact measurement you would record on an instrument. However, physical systems rarely sit in one definite state. When outcomes are probabilistic, we calculate an expectation value. This metric provides the average result we would expect to see if we measured the identical system thousands of times. By sandwiching the operator between a bra and a ket, we create a single equation representing the weighted average of all possible realities. Together, these two mathematical structures equip physicists to handle both the certainties and the statistical probabilities of the quantum environment. This grammar culminates in the foundational sentence of quantum mechanics, the time-independent Schrodinger equation. Look at how it reads.
The Hamiltonian verb acts on the quantum state noun, and the result is a measurable energy eigenvalue tied to that state. Solving this specific mathematical sentence allows researchers to determine the precise electron bands inside solid materials and molecular orbitals. These equations provide the functional blueprints for our hardware. By isolating Hamiltonian operators, engineers calculate the exact electron energy levels required to design semiconductors. By mapping spin operators, they predict how atoms respond to the magnetic fields inside an MRI. Because the notation isolates the abstract state at the center of the equation, it functions as a universal interface. Researchers can shift descriptions between different coordinate systems, like position and momentum, without altering the underlying identity of the quantum system. Once researchers can fluently read the grammar of quantum mechanics, they can physically design the materials that drive modern civilization. The current evolution of Dirac's language is quantum computing, where these mathematical concepts operate as literal hardware components. Inside a quantum processor, qubits are kets maintained in physical superposition. They hold information not as binary bits, but as complex state vectors. The physical logic gates firing inside the processor are the operators, performing real-time matrix transformations to entangle or flip qubits according to the notation's rules. Mastering bra-ket notation moves physicists from passive observation to active manipulation. This grammar provides the precise instructions required to program the physical world at the atomic scale. This abstract grammar bridges the critical gap between theoretical matrix algebra and the physical future of information technology.